I have taken up another simple problem on Thevenin's theorem. This doesn't have any dependent source. It has only three independent sources, voltage sources. And the problem says find the current through 2 ohm resistor using Thevenin's theorem. The idea of taking up this problem is to tell that there are several ways of doing the same problem. In any network analysis problem can be done by several techniques, several methods are there. So here we are supposed to find out the current through 2 ohm resistor using Thevenin's theorem. Had the method not been mentioned, we could have done it by different techniques. Like we could have done it by source transformation and then finding out the current through 2 ohm, simplifying the network. Or we can do by superposition or by mesh current analysis. You can do it by nodal analysis. There are several techniques. But here in this problem, the method mentioned is Thevenin's theorem. Let us try to approach this problem with the same method. Okay, so how do we do? What is Thevenin's theorem is about? Thevenin's theorem talks about replacing the entire network by a simple voltage source between any pair of terminals. Now in this problem, what is that pair of terminals we are talking about? We are talking about 2 ohm resistor, current through 2 ohm resistor, right? So 2 ohm resistor is connected between a pair of terminals. So we identify that pair of terminals. We will try to name them. Let me call this A and let me call this B. So between A and B, 2 ohm resistor is connected. So if we have to find out the current through 2 ohm resistor, we need to initially find out what is the Thevenin's equivalent circuit between A and B. Later on, we can connect back this 2 ohm resistor and find out the current through it. It is as simple as that. But then initially, we need to find out the Thevenin's equivalent network between A and B. These are the two terminals under consideration, A and B, right? So what is the step? We try to find out the open circuit voltage between A and B. That's number one. That will be the magnitude of the Thevenin source. And number two is we try to see what is the resistance offered by this entire network between A and B. So that is the Thevenin's equivalent resistance. So once we find open circuit voltage, which is a Thevenin's voltage, and the equivalent resistance between the pair of terminals, that is A and B, we are done with Thevenin's equivalent network, which is nothing but a simple voltage source. So let's go about this problem now. So first step, let me write down the step number 1. I will write it only instead of typing. Step 1, the first step is to find Thevenin's open circuit voltage. Okay, Thevenin's voltage is nothing but the open circuit voltage. So where do we find the open circuit? We need to create an open circuit between the pair of terminals under consideration. That is A and B of this network. So I will reproduce this network. I'll pick it up. I picked it up. Then I'll paste it here. Okay, so I've pasted this network. Now I have to create an open circuit. Where do I create an open circuit? I create an open circuit between A and B. I've removed this element A and B. Okay, this 2 element is being removed. An open circuit gets created now. And what we try to see is what is this open circuit voltage? Between A and B, what is the voltage that appears in the network? Right, so we can find out this voltage by different techniques. Let's go by, let's say, mesh method. For a change, I will try to choose a color for the current representation. I can see in this network 3 meshes. All right, so current flows in closed paths or meshes. So I'll call the current here to be I1. Okay, the current in this mesh, I call it as I2. I assume clockwise directions conventionally. And here, again, I can assume clockwise direction, but then this mesh being, you can see the polarity. It is a DC source. Current flows from positive to negative. So I would assume a current in this direction. It doesn't matter. I can assume a clockwise direction, and then I found that magnitude of current I3 to be negative, and then I will reverse and put back the current in the anti-clockwise direction. It hardly matters how you assume the direction of current. All right. So having assumed the current will not flow here in this along this wire, the current will not flow because there is no return available. So current would circulate here, it will circulate here in this closed path, current would circulate in this closed path. There is no closed path comprising of 30, 45 and this 30 ohm resistance. There's no closed path. So obviously here is an open circuit. So we will be able to develop a voltage between A and B that we will try to find out. So our first objective is to find these three currents. Alright. So I3 current is circulating in this loop. So what is the magnitude of I3 current? It is very, very simple. We try to apply Ohm's law. The voltage that is available in this loop is 40. And the total resistance, these two are in series. How do we say they're in series? Whatever current flows through this 30 also flows through this 30. Whenever current through any two resistors is same, we say that the resistors are in series. It is as simple as that. So we can simply find out I3 by Ohm's law. But then for I1 and I2, we may require mesh equations. Alright. So we will try to write this information that we have now understood. Okay, let's try to find out what is I3 on one side. So I3 is simply equal to 40 divided by 60. 40 volts divided by 60 ohm resistance. This is coming out to be 0.67 ampere. We can calculate and you know I3 now. Okay, so I3 is, this is an important result. We would require this result to compute the potential difference between A and B, which is nothing but our open circuit voltage. So we will put it in one rectangle so that it's available to us for future use. Now we will go back to the equations. Okay, so we'll try to write mesh equations for the two meshes, 1 and 2, carrying currents I1 and I2 respectively. How do we do that? Sorry there. How do we do that? So we will try to combine all the resistances that would come under mesh 1, that is 75 plus 15. I suppose that is 90. 90 ohm resistance. I1 is the current. The resistance that is common between mesh 1 and mesh 2 is 75 ohm. This is 75 into I2. This is equal to 75 volt. This is I'm trying to write the mesh equation by inspection. This is mesh equations by inspection. So if you cannot write it by inspection, you can write it by first principle. It doesn't matter. You have to get the same equation at the end of the day. Alright. So coming to the mesh 2, what is common between mesh 2 and mesh 1? That is 75. That will get minus 75 I1 plus the sum of the resistances in the mesh 2. So it is 75 plus 30. I think that's 105 I2. And this is equal to minus 45. So if you're not able to do this, you can write simple equations and then you can arrive at it. What I mean is you can start from one end. I will show you as to how to write that also as a side note. So what I mean is we can start from this end of the mesh. We can go along this, come back here and come back here. Write one equation and again you can start from this end of the second mesh A, go via 30, go via 45 and 75 and come back. You can write simple KVL equations. We will write that also so that you will understand how 1 and 2 we are able to get. The equations 1 and 2 we are able to get. Okay. So what I mean is we will write this as the equation 1 and 2 can also be obtained this way. 15, the current that is flowing is I1, that is drop in voltage. Then we come via the diagonal. The diagonal has got 75 ohm resistance. The current along the clockwise is I1 minus I2. And we hit the negative sign of the source, minus 75 equal to 0. So you simplify, you'll get equation 1. Okay, equation 2, how do we get equation 2? We write the KVL equation for mesh 2. That is 30 ohm resistance carrying a current of I2. Then plus 45, that is drop in potential of the source. You are coming from positive of the source to the negative of the source, that is plus 45. Drops are positive, then we come here, then we go here 75. Then plus 75 into the direction of current now clockwise is I2 minus I1 equal to 0. So these are the two mesh equations, KVL equations. You simplify, you will get the same equation 1 and 2. So without writing these things, we are able to write it by inspection. That's it. Whichever way is convenient to you, you can do it. So the latter way, that is writing the equation in this manner, you will not make any mistake. This way there are chances that one may make mistake. Anyway, So the point is when we write the equations of for the two meshes, then we try to evaluate the currents. So one can always find out what is I1 and I2 because we have two equations and two unknowns. So we have a scientific calculator at our disposal. So it's very, very simple to evaluate. So you can do it by Cramer's rule. So what I mean is I1 can be evaluated. I will put it Cramer's rule. I'll try to put. So this is 75. You can look back into my previous videos wherein I have even given explanation of Cramer's rule. So it's up to you what you want to do. If you know it, it's nothing like it. It's very, very simple rule. There is no great deal about it. So we try to evaluate I1 in this manner. It is the ratio of two determinants. The denominator determinant is what we call as discriminant, and this comes out to be 1.18 ampere. Okay, so you know how to expand the determinant. I don't think I need to tell that. That means this into this, minus of this into this. This is going with a negative sign. So divided by this into this and negative of this into this. That will give you. Okay, so or else I'll put that. I'll put that once for a change. I'll put that. So that when you watch the video, if you have that confusion, or if you don't remember in time, this will help you. So what I mean is this is evaluated as 75 into 105 minus, this is minus 75 to minus 45. Okay, that's how we expand the determinant. The denominator we do 90, 105 minus 75 minus 75. We can do this computation. This comes out to be 1.18 amperes. Okay. Similarly, if you do I2, how do we do I2? I2 is evaluated by replacing the second column of the discriminant. What do we mean by discriminant? This is our discriminant delta. This is delta. Okay. So we replace the second column of the determinant delta by 75 45 minus 45. Okay. While evaluating I1, what did we do? In delta, we replace the first column by 75 and minus 45 in the numerator. Okay. So what I mean is I2 is evaluated as, this is 90 minus 75 of delta is retained, and these two values are replaced by the right hand side terms. This determinant divided by the same delta determinant that we have evaluated in stage 1. That is, this is 90, this is 75 with a negative sign, minus 75, 105. So this again is expanded, then you will be able to get this to be 0.412. Okay, amperes. So we are able to get I1, I2, I3, all the three currents we are able to get. Okay, now what do we do? I'll try to reproduce the circuit again. I will try to take this circuit again. I need to be a little careful in marking this circuit. Okay, I'll copy this. I'll put back here. I'll paste it here. And now I'll try to have all the currents written down so that the computation becomes easy. So what have we got? We have got I1 to be equal to 1.18 ampere. This is what was calculated previously. You can look back and find out. And I3 we have computed it to be 0.67 amperes. Alright. So these are the three currents that we are trying to have in the circuit. Now how to get the potential difference VOC? See, the technique is you go from potential A to potential B, try to add up all the potential differences. Alright, so the convention is that we try to take the drops positive. The convention, let's recollect once more. Voltage drops are given a positive sign. Voltage gains are given a negative sign. Okay, this way we do. Okay, so how do we do? So we are supposed to find out VAB. What is the potential difference appearing between terminal A and terminal B? This is in fact is the open circuit voltage, which is also called the Thevenin's equivalent voltage. All the things are same. Okay, how do we do? We will go from A to B. We will go from A to B along this path. You can take any path. You can start from A, go via this, come here, go via B. You can go from here to here to here to here and to here. That way also you can go. All you have to do is you have to go from A to B via any path that you choose. Let me try to take A to this point, and then this shortest possible route. Let's try to take. Okay, so if I start from A, I go to 30 ohms. The direction of flow of current I2 is downwards. Because I was able to get I2 to be positive, I am able to get I2 to be positive, which goes to say that the assumed direction of flow of current is correct. So current is flowing from A to via 30 via this to this terminal, right? The current flow is downwards. So I'm also going in the downward direction. That means I'm encountering a drop in potential. So I have to take a positive sign. All right. So I'm repeating these things for the benefit of those who are seeing this video only independently, right? They should understand something at least. This is 30 into I2 is the drop in potential, resistance into current, I into R. Rather, R into I have taken, okay? Resistance of 30 ohms, I2 is the current. Now I hit the source, which is 45 volt potential difference. So I am going from top to bottom. I am hitting the positive sign, that is positive to negative drop, and that would be plus 45. Then I have come back to this common terminal, and now I am going upwards from this common terminal to B. So my direction of movement is in the upward direction, as the current actually is flowing from B to downwards. From B downwards, it's flowing via 30 ohms. So my direction is opposite. So it is gain in potential. I'm encountering a gain in potential because this terminal is at the negative potential, whereas B is at the positive potential, because current flow is from B to this common wire. All right. So now I will have to put a negative sign. So what is the magnitude of the potential difference? Magnitude of the potential is 30 multiplied by the current I3. So we have the values of I2 and I3 from this table. We can pick up I2 and I3. We can substitute here. So we can get the magnitude of VTH. Let me put this as 0.412 plus 45 minus 30.67. If I simplify this, I will get it to be 37.26 volts. This is my open circuit voltage. Okay, so the Thevenin's voltage is now 37.26 volts. Okay. All right, so we are able to get the Thevenin's voltage. Now, what is the next step? So we need to get the Thevenin's resistance, equivalent resistance of the Thevenin's source. Okay, so I'll try to take this also, put it here. Now, so the next step is to get the Thevenin's equivalent resistance between A and B. What do? In order to find out the Thevenin's resistance between A and B, we deactivate all the sources and view the network through these terminals under consideration and find out what is the equivalent resistance this network has to offer. Okay, so we will try to do that. I will try to pick up this network again. I'll try to pick up this network. This I'll copy again and I'll paste it here. Now what I do is I'll remove all these things, the currents, etc. The things that I have marked I'll remove so that it doesn't cause any confusion. Okay, now this also I will remove. Everything I've removed. I have maintained only A and B. So what's my step 2? This step is I'm trying to do in step 2, I'm trying to find out the equivalent resistance. between A and B. This is nothing but RTH. This equivalent resistance is what we call as RTH, the Thevenin's resistance. So what am I supposed to do? I'm supposed to deactivate all the sources. Okay, these are all independent voltage sources. Deactivation of voltage source would mean you must be able to get zero potential difference across the source. So you have a voltage source, right? If you connect a voltmeter between the two sources, whatever is the magnitude, let us talk about the 75 volt. If I connect a voltmeter here, this would record 75 volts. Okay, even though I have not connected anything between the pair of terminals, no load is being connected, it is recording 75 volts. That means open circuiting a voltage source would still be considered on. The source is on. The source is not off. Okay, so we have to understand this thing very carefully. So what do we mean by off condition of the source? Off condition of the source means instead of connecting a voltmeter which has got enormous high resistance, we try to keep it, we short it here. Suppose you short the source. I mean, what I mean is this is a representation. Actually, physically, when we do the experiment or when we deal with the source, we switch it off. It is as simple as that. The switching off condition, when the source is switched off, so even if we connect, this is off, if this is off, even if we connect a voltmeter here, this will record as 0 volts. Alright? So if we switch it off, you record a 0. That means the switching off condition should give 0 volts. So switched off condition obviously would mean a short circuit, because if across a short, if I connect a voltmeter, what do I measure? I'll measure 0 volts. So hence switching off condition of a voltage source is represented by a short circuit. So we need to understand this more than remembering this. Okay, switching off condition of a voltage source means replacing the source by a short circuit. That is what we will do. So I will remove this. Wherever there is a source, I have removed the source. The 45 volts is also removed. The 75 volt is also removed. I have removed all the source. I cannot keep it open. If I keep it open, you will get the potential difference. So what we do is we will replace it by a short. I'm using a pink line. Okay, I have shorted all the sources. I've replaced the sources by a short circuit. You should know why we replace it by a short circuit. Okay, so now this is my A, this is my B. Now I'm trying to view the network in this manner. So if I view the network, what is the resistance this network has got to offer between A and B? What I mean is, if I imagine a source between A and B, what is this entire network would offer as impedance? What impedance is offered by this entire network is what I mean by R equivalent, right? So if I see this way, so the impedance, one can easily see this 15, this 15, this 75, this 30. They're all in parallel, because current, if I imagine a source between A and B, A being at higher potential or a positive terminal, current would enter here. It has to come back to this end. It has got one path, two path, three paths. Okay, so one end of 15, 75, 30 are connected here. The other end of 15, 75, 30 are connected at this common end, right? So these things are in parallel. So these three would be in parallel. Similarly, 30 and 30 would be in parallel. That again thing would come in series. Alright, so what I mean is this network is same as, I will write one more step for better understanding. So I will put one equivalent resistance here and one equivalent resistance here, and this is my A and B. This is my A, this is my B, this is 30 parallel 30. Okay, whose value is half of 30. It is a simple fundamental rule that we have deduced long ago in elementary course on electrical engineering. This would be 15, parallel 30, that parallel 75. So one can always find out. How do we find? This is 15 parallel 30 parallel 75 is 1 divided by 1 over 15 plus 1 over 30 plus 1 over 75. We find it this way. Okay, this is your parallel equivalent of 15, 30 and 75. Okay, that one can always compute from some fundamental parallel circuit concept, and this comes out to be equal to, this entire thing would come out to be equal to 8.82. This parallel combination would come out to be 8.82 ohms, and this is 15 ohms. All right, now what is ZTH or RTH? Therefore, RTH, the equivalent resistance as seen from the network, this is RTH. I mean, RTH equal to 8.82 plus 15. This comes out to be my 23.82 ohms. All right. So having found the RTH value, what we have now is to write down the Thevenin's network. Okay. So how does the Thevenin's network look like now? So therefore, the Thevenin's network between A and B, we will write a statement. Therefore, okay, so how do we write the Thevenin's equivalent network? So it's simple voltage source. This is my voltage source. I have a resistance in series with this voltage source. Now this is A and B. I'll put the values. This is my RTH, 23.82. This is my A, 23.82 ohms A. This is my B. This is my VTH. VTH, how much is VTH? It is, I suppose, 37.26. Positive, negative. Okay. Now my 2 ohm is connected here. I'll take my 2 ohm resistor, which is connected originally between A and B, which we opened it for calculation of Thevenin source. Okay, this is my 2 ohm resistor. I've connected it back. This is my 2 ohm resistor. So the problem says find the current through 2 ohm resistor using Thevenin's theorem. Now it's a simple series circuit. So what is the current through 2 ohm resistor? If I can designate this as I through 2 ohm, I through 2 ohm, it's very simple. I through 2 ohm is equal to, what is the total voltage in the circuit? That is 37.26 is the total voltage. And what is the total resistance of the circuit? It is RTH plus 2, that is 25.82. Okay, this comes out to be equal to 1.44 amperes. And that completes the problem. Okay, so 1.44 amperes is the current through two ohm resistor. Given in the circuit. So that would be the end of this video. Okay, so I have taken up a simple problem, thinking that, a simple problem is also sometimes, it may be difficult for learners, right? Beginners rather. So a quick recap, what have we done? So we are supposed to find out the current here. The current through 2 ohm resistor is the objective. We could have done by different methods, but however the method suggested here is using Thevenin's theorem, a very popular theorem. Okay, the entire network between A and B gets replaced by a voltage source, and you connect the whatever is the load, you connect, and then you find out the current through it. That is Thevenin's theorem. Any network can be replaced by a simple voltage source between a pair of terminals. Okay, so that is objective. So whenever you need to find out the current through any particular branch of a network using Thevenin's theorem, what you have to do is you have to find out the Thevenin's equivalent network between the pair of terminals under consideration. Okay, so if I am supposed to calculate the current through this 2 ohm, I'll identify the terminals between which you have this 2 ohm, that's A and B. Then I will go step by step. First step is to find out the open circuit voltage. So open circuit voltage, you create an open circuit voltage and find out the voltage. And second step, you find out the resistance between A and B. In both the cases, A and B is kept open. Okay, it's a simple series parallel arrangement, simple resistances are there. The concept can be extended to impedances also. What is true for resistance is true for impedance. So impedance would involve complex calculation. You have to be little skillful in doing it correctly. That's all. Beyond that, concept wise, there is no big deal. Okay, so you replace the entire network between A and by a Thevenin source, which has a voltage magnitude in series with a resistance. This is a practical voltage source, right, between A and B. What we mean is this entire network, this entire given network, this network between A and B can be seen as a voltage source. This is the source. This is the voltage source. Where have we written? This is the voltage source, right? So we connected back this 2 ohm. Instead of 2 ohm, you can even calculate, if you can replace 2 ohm by 8 ohm, you can calculate the current there. So any current can be evaluated, right? So that way we try to work out the solution to the problem. The idea is, instead of 2 ohms, if you want to change that particular branch current, you are interested in finding out suitable value, for the resistance, or you are trying to compute the power consumed. Whatever may be your objective, you want to, change the values of some load for some purpose. So you can easily now change this without having to calculate any other value. It is so simple. Now the circuit has become a voltage source, one can always calculate. So that is the best part of Thevenin's theorem. So I suppose I have made myself clear. See you in more videos. I suppose I'll stop with Thevenin's theorem. Maybe I'll do maximum power transfer theorem. There's no, there's no need to compute, do problems on Nortons, because Thevenin's and Nortons are, duals of each other. If you have understood the Thevenin, you might as well do Norton, right? So maybe I'll see if there is any request from any viewers, I'll make videos on Nortons. Otherwise, I'll move on to maximum power transfer theorem. Thanks for watching. I really appreciate your viewership. Any suggestions, any typical problems can be even posted so that I can provide solution, an elaborate solution. Thank you.